All right, this lesson is about all of the rules. We call them differentiation rules that helps us find the derivative of functions like power functions and constant functions, polynomial functions, rational functions, and even combinations of them without having to take the limit each time. Taking the limit each time using the definition of a derivative function requires us to take the limit as h goes to 0, right? And doing that sometimes takes some time and some work. Well, these rules are going to help us find the derivative function fairly simply and actually directly. So this is going to be really great for us for finding derivative functions. So let's start with the derivative of a constant function. All right, so the first one we have, if f has the constant value c, if f of x is always c, then the derivative of function f with respect to x is the derivative of this constant with respect to x, which is just 0. We know that the graph of a constant function is a horizontal line at y equal to c. So this rule that says that the derivative of a constant is always 0 is just, another way to say that is that, the value of this function is never changing. The value of this function is always c. And that is to say the slope of this line is 0 at every single point. So if you start at this point, x comma c, and if you move h units maybe to the right, let's say, the function value is still c. So no matter what point you consider in the domain of this constant function, the function value is always c. Remember that we define the derivative as the slope at any point, right, along the curve. And so no matter what point you consider, the slope is going to be 0 because this is a horizontal line. All right, now the derivative of a positive integer power. So this rule we're going to use so often. If n is a positive integer, then the derivative with respect to x of this expression, your variable raised to this positive integer value, and this is your variable x raised to the power of n, is simply equal to n times x to the power of n minus 1. So notice that this power n becomes the coefficient of your variable. It like comes down, if you will, in front of x. And now the power is decreased by 1 unit. As a matter of fact, we actually can extend this rule to include any real number power. Let n be any real number, then this rule actually applies. And so this is true not just for positive integer values of n, but even negative values for n, or even a fractional power. N could even be irrational, right? So this rule, this is the more general version of the rule where n is any real number. All right, folks, let's go for it. Let's start differentiating. So here I've given us x cubed. So according to the rule, let's practice using proper notation. And so what we're going to say is the derivative, so d dx of x cubed. So I encourage you to use proper notation. Okay, don't just apply the rule, but actually use this notation, d dx, okay? The derivative of this expression with respect to x is what we're saying. So it's equal to, the power comes down, so now it's 3 times x to the power of 3 minus 1. So then the derivative is 3x squared. Folks, we are done. That's it. That's how fast we can find the derivative of this function. Isn't that great? Now, if we don't use this this rule, then the derivative is going to be the limit, right, as h goes to 0 of x plus h quantity cubed, right, minus x cubed all over h, and we need to expand now this this binomial and and do all the work. But at the end of the day, after you do all of this algebra right here, et cetera, et cetera, et cetera, you're going to find that the answer, the derivative, is just 3x squared. So I just want to highlight how fast and how efficient this is now, finding the derivative of a power of x using this power rule. So this is, I hope you're excited as I am. I hope you're really grateful for this rule for finding the derivative function. So this is really great. All right, here's our new expression, x to the power of 2/3. So this is a fractional or rational power of x. We can definitely use our power rule. So let's go for it. So d dx of x to the 2/3. Again, I recommend that you use proper notation, and that is 2/3. All right, great. So 2/3 comes down, right, folks? And then now you have x to the power of 2/3 minus 1. So then the derivative is 2/3 x to the power of negative 1/3, right? Awesome. We're done. It's that fast. This is the derivative of x to the power of 2/3. If you wanted to, the negative exponents reciprocate your base. And so what this can be rewritten as is 2 over 3x to the 1/3. That's an equivalent way of writing this expression. All right, moving right along, x to the power of the square root of 2. This is an irrational power of x. We can definitely use our power rule. So d dx of x to the power of root 2. All right, so root 2 comes down, and now this is x to the power of root 2 minus 1. Root 2 minus 1 is root 2 minus 1. You cannot simplify that. Remember, root 2 and minus 1, they're like, one's rational, and then this number is irrational, so there's really no way to simplify that, so it is what it is. Make sure that this x is not underneath the square root with the 2, So this is the square root of 2 times x to the power of root 2 minus 1. All right, now we have 1 over x to the 4th. What I recommend is to rewrite this first. Before you actually find the derivative, I recommend that you rewrite this as x to the power of negative 4. So this is really, in essence, it's us finding the derivative of a negative power of x. All right, very good. Now that we wrote it like that, we know that the derivative with respect to x of this expression, x to the negative 4, is equivalent to negative 4 x to the power of negative 4 minus 1. So then it is negative 4 x to the power of negative 5. This can be rewritten as negative 4 over x to the 5th if we want to write it with a positive exponent. Be careful when you write your final answer here. Negative 4 is not part of the base, so negative 4 is not going in the denominator of your expression. X is the only base of your negative exponent, so it's only x that goes downstairs, right, into the denominator. Be careful about that. All right, we're just going right through these. So now we have a negative rational power or negative fractional power for x. All right, so let's go for it. So the derivative of x to the negative 4/3 using the power rule is pretty simple, right? So negative 4/3 times x to the power of negative 4/3 minus 1. So then this is negative 4/3 times x to the power of negative 7/3. And we can rewrite this if we choose to as negative 4 over, actually I would prefer to write this negative right here in front of our fraction. So negative and then 4 over 3 to the power of, 3 times x to the power of positive 7/3. So this is the derivative function. Very good, folks. Okay, the last one like this, and of course it's probably the more complicated one. We have the square root of x to the power of 2 plus pi. All right, so before we actually calculate the derivative, or before we actually differentiate, I want us to consider, let's consider rewriting this, because we want to consider this to be x to the power of something, right? In order to use the power rule, what is x being raised to? I mean, in this expression, I'm not really a big fan of how this is written, is because x is being raised to the power of 2 plus pi, but it's also being raised to the power of 1/2 because of the square root. So I want to rewrite this so that I have just x raised to some power. So, we can rewrite this as x to the power of 2 plus pi, right? All of that raised to the power of 1/2, because that's how we interpret the square root. And now, by the power rule for exponents, we know we're supposed to multiply these powers. And so then this is x to the power of 1/2 times 2 plus pi. Okay, this is looking better already. So now distributing 1/2, I get, this is really x to the power of 1 plus pi over 2. Okay, now I can see x by itself, right? Just x here, now being raised to the power of 1 plus pi over 2. All of this is a irrational power. Irrational because pi is irrational. So irrational power. All right, now let's find the derivative. So the derivative with respect to x of x to the power of 1 plus pi over 2, like that. All right, very good. Now remember that that power is irrational. So here we go. Bring down the power. 1 plus pi over 2 is the power. Put that in parentheses because it's more than one term, right? Times x to the power of 1 plus pi over 2, now minus 1, according to the power rule. We should simplify this as 1 plus pi over 2 times x to the power of pi over 2. All right. Okay, very good. If we want, we can rewrite this so that it looks a little neater, or more simplified. You can factor out a 1/2 right here from this expression, so that we don't have a fraction. If you factor out 1/2, then this is 2 plus pi. That looks nice, right? If you factor out a 1/2 from both of these terms, we know we're right, because if you distribute 1/2, half of 2 is 1, and half of pi is pi over 2. And then furthermore, this is pi over 2, so this is really 1/2 times pi. And that 1/2, let me bring this down just a little bit, or move this up rather, just a little bit. That 1/2 right here, power, is really the square root. So we can rewrite it as 1/2 times 2 plus pi. And then we can say the square root of x, let's write it like this, the square root of x, and x is really being raised to the power of pi. This pi right here, the power of pi, can be written on the radicand, or it can be rewritten on the, let me show you, if I can, it can be rewritten like this, the square root of x and then raised to the power of pi. I don't like all of those extra, like, the parentheses and stuff, and so I think it'd be neater, if pi were just written on the radicand like that. All right, very good, folks. All right, our next rule is the derivative constant multiple. The derivative of a constant multiple. So if u is a differentiable function of x and c is a constant, then the derivative of c times u, the constant, so this is a number, times your function, is equal to that constant times the derivative of u with respect to x. So for example, if we're differentiating 3x squared, all this really means is that the derivative of 3x squared with respect to x, we're basically using two different rules here. This is equal to 3 times, and then the derivative of just x squared. Let me use some extra parentheses here. The derivative of x squared. So 3 times the derivative of x squared. And so this is 3 times, and then we know what the derivative of x squared is by using the power rule. It is 3 times 2, x to the power of 1. So then this is really just 6x. This is the derivative of 3x squared. All right, this next rule is the sum rule. And it basically says that the sum of two differentiable functions is the sum of their derivatives. So the sum, the derivative of a sum is equivalent to the sum of the derivatives. It says here, if u and v are differentiable functions of x, then their sum, u plus v, is also differentiable at every point where u and v are both differentiable. I like to say it like this: the derivative of a sum is equivalent to the sum of the derivatives. Now, this rule also applies to subtraction. And so you can also have the difference rule. That is to say, the derivative of a difference is equivalent to the difference of the derivatives. All right, very good. So now let's look at some additional examples. All right, we want to find the derivative of this polynomial. Y equals x cubed plus 4/3 x squared minus 5x plus 1. All right, so what we're asked to find is dy dx. dy dx, again, I'm encouraging proper notation here. Dy dx is the derivative of y with respect to x, which is what they're asking us to find. How are we going to find that? We're going to find it by evaluating the derivative of x cubed plus 4/3 x squared minus 5x plus 1 with respect to x. Now, this is written as both a sum and a difference, right? And so we know that the derivative of a sum is equivalent to the sum of their derivatives. Also, the derivative of a difference is equivalent to the difference of the derivatives. In other words, this is equivalent to the derivative of x cubed plus the derivative of 4/3 x squared minus the derivative of 5x plus the derivative, if I can squeeze this in here, the derivative of 1. All right, and now we're just using for the derivative of x cubed, we're using the power rule to say that this is equivalent to 3x squared plus, here we're using both the power rule and the constant multiple rule to say this is 4/3 times 2 x to the power of 2 minus 1, which is 1, minus 5, right, plus 0. Remember that the derivative of just a constant is 0. Let's simplify. So then this is 3x squared plus 8/3 x minus 5. This is the derivative of y. This is y prime, right? Y prime, or dy dx. All right, cool. Let's look at this example. Does the following curve have any horizontal tangent lines? If so, where? Now, this is the idea here. I like this problem a lot. The idea here is if this curve has any horizontal tangent lines, that means the derivative of this function, this quartic polynomial function, the derivative would have to be equal to 0. Why? Well, because the derivative describes the slope of the tangent line at this curve, the tangent line of this curve. And if the tangent line's horizontal, that means the slope of that tangent line is equal to 0. So this is the idea. Let's find the derivative of this function. Once we find the derivative, we'll set that derivative equal to 0 and solve. If we find a real number solution for that equation, then the answer is yes. This curve has horizontal tangent lines, and we can say exactly where those tangent lines are located. All right, so I hope that makes sense. Let's find dy dx. That is to say, let's find y prime. So dy dx is equal to the derivative of x to the fourth power minus the derivative of 2x squared plus the derivative of 2. Now, right there, I already used the sum and the difference rules. All right, the derivative of x to the fourth is 4x cubed. That's the power rule. Minus, and I'm going to use the constant multiple and the power rule to say that the derivative of 2x squared is simply x. This 2 here in the power would come down. Oop, and I made a mistake. Sorry about that. And when it comes down, it is, let me find my eraser. There we go. It's 2 times 2, which is 4, and now x to the power of 1, because 2 minus 1 is 1. Moving on, this is plus 0. Oh, okay, so I won't write it, but it's plus 0 because the derivative of a constant is just 0. Okay, folks, now what we need to do is we need to solve this equation. Dy dx is equal to 0. Again, we're setting it equal, the derivative, that is, the derivative function, equal to 0 because they're asking us about horizontal lines, horizontal tangent lines. Horizontal tangent lines means the slope is equal to 0 because the slope of any horizontal line is 0. And the derivative function describes the slope. So we're setting the derivative equal to 0. So then this is implying that 4x cubed minus 4x. When is that 0, right? When is that 0 is the question. All right. So then let's solve for x. What can we do? Oh, we can factor out of 4x, leaving us with x squared minus 1. Oh, this is really good. All right. So then we can just set each factor, equal to 0. So 4x is 0, or x squared minus 1 is 0. So then this is x is equal to 0. This is x squared equal to 1. And using the square root property, x is equal to plus or minus 1. So the curve does have horizontal tangent lines. We're at x equal to 0, x equal to 1, and x equal to negative 1. Let's find the actual points. Where the horizontal tangent lines occur. So let's see, I'm going to change this color here. So remember that our curve is x to the fourth power minus 2x squared plus 2. Let me move the screen up. So when x is 0, we have a horizontal tangent line to our curve. So when x is 0, notice that your y value is 2. So right at that y-intercept on the graph, there's a horizontal tangent line. Also, when x is 1, right, then we have another horizontal tangent line. Notice that when x is 1, y is, 1. Go ahead and plug 1 in, right? So at 1, 1. Also, when we plug negative 1 in, right, we get 1 out, positive 1 out. Let me do that math really quickly. Yeah, we're good. So then at these 3 points, our curve has a horizontal tangent line. Let's graph really quickly our curve, and we can see a graphical representation for what we're talking about. I'm going to move our board up a little bit. Remember that this is just a polynomial function. You remember, I hope you remember how to graph a polynomial function. The end behavior, because the leading power is even and the leading coefficient is positive, I know the end behavior is both, up on both ends there. I also know that the y-intercept is 2. All right. So with more inspection and investigation, you can find the zeros of the function. And if you do, you'll find that there are no real number solutions for this polynomial, meaning that there are no x-intercepts. So you can find that. But anyway, this is the, let me see if I can erase this end behavior really quickly. This is what the curve would look like. Here's our curve for, I can label it, this is y is equal to x to the fourth minus 2x squared plus 2. But what we just found is that at the point negative 1, 1, which happens to be a local minimum, and I'm getting ahead of ourselves here a little bit, but we're going to find that this is a critical point here because the slope of the tangent line, that is to say the derivative, is equal to 0 here. The tangent line's horizontal. And negative 1, 1 is a critical point. Also, at 0, 2, that was horribly drawn. Let me see if I can do better. Yeah, I can do better. Another horizontal tangent line, and then another horizontal tangent line. There, I got it. So this is the graphical representation for the work that you and I have just done. And notice again that this is a minimum. This point right here, negative 1, 1, is a local minimum. It's also an absolute minimum. So is this one. It's a minimum. This one here is a local maximum. It's not the absolute max because there is no absolute maximum. This function keeps on going up forever, right? But it's a local maximum. So notice that the curve has horizontal tangent lines, or that is to say the derivative is equal to 0 at the minimum values and the maximum value. I hope that helped just to see the graphical representation. All right, let's look at the product rule, the derivative product rule. All right, we have the derivative product rule. All right, because there's a lot of product rules in mathematics. There's a product rule for exponents, product rule for logarithms, product rule for radicals, so many different product rules. This is the product rule with respect to derivatives. If u and v are differentiable at x, then so is their product. Okay, folks, so the derivative of this product, u times v, where u and v are functions of x, then it is equal to, the derivative of this product is equal to u dv dx plus du dx v. In other words, it's function u times the derivative of v plus the derivative of u times v. So in prime notation, if it's more straightforward in prime notation, we're saying the derivative of uv, right, is uv prime plus u prime v. Okay. In function notation, if you prefer to see function notation, the derivative of the product of these two functions is equal to f of x times g prime of x plus f prime of x times g of x. So we multiply f here in prime notation with and function notation here. We multiply f by g prime, and then we multiply g by f prime. All right. These are just, 3 or 4 different ways of saying the same thing. So whichever, way helps you better understand the rule, then I would say gravitate toward that notation. One thing I would like to stress is that notice that the derivative of a product is not the product of the derivatives, right? We said that the derivative of a sum is equal to the sum of their derivatives. We said the derivative of a difference is equal to the difference of the derivatives. However, when it comes to multiplication, the derivative of a product is not equal to the product of the derivatives. In other words, we did not say that the derivative of this product is simply u prime times v prime. That's not true. So I don't know if it's helpful to add this to your notes, but the derivative of a product is not equal to the product of their derivative. So the derivative of this product is not equal to u prime times v prime. Okay, so sometimes I think it's tempting to say that maybe because we found that the derivative of a sum is equal to the sum of their derivatives. So the derivative of a difference is equal to the difference of their derivatives. But you cannot extend that to multiplication. All right, let's find the derivative of y, the derivative of this function. Y is equal to x squared plus 1 times x cubed plus 3. So notice that we are given a product, right? So we can actually use our product rule. So this here in your notation, this is really u and this is v, right? And so we know that the derivative will be u times v prime plus u prime times v. That's going to be like our pattern here, all right? So let's actually do that. So we have dy dx is equal to the derivative, again, I want to stress proper notation, the derivative of this product. There. All right, I got it. All right, so let's go for it. So then it'll be, remember, this is like your, in the definition, right? This is x squared plus 1 is like your u, the first function, and then x cubed plus 3 is like your v. Or if you prefer, this is like your f, and then the second one is like your function g. All right, so let's do it. So it'll be x squared plus 1, that's the first function, times the derivative of v, the derivative of the second function. Now, the derivative of x cubed plus 3 is the derivative of this sum is equal to the sum of their derivatives. So the derivative of x cubed, that's the power rule, that's 3x squared. And then the derivative of 3, that's a constant term, so that's just 0. So the derivative of that second function is just 3x squared. Now, plus the derivative of the first function now, which is just 2x, right? Times the second function. Cool. So then this is 3x to the fourth power plus 3x squared plus 2x to the fourth power plus 6x. Writing this in descending power order and combining like terms, this is 5x to the fourth power plus 3x squared plus 6x. Good job. We found the derivative of a product. Now, I do want to say, I think it's worth saying that we could have found the derivative by first actually expanding this, like multiplying these two binomials, and then just finding the derivative of the resulting polynomial. In other words, let me see if I can do that really quickly for us. If I can just get rid of what I've written so far. You know, we could have rewritten this as, multiply, distribute this, and this would be x to the fifth, right? Plus x cubed. I'm trying to write this in descending power order. 3x squared plus 3, like that. This is what y is. And so if we would have written it that way, then finding the derivative, dy dx, it'll just be the derivative of a sum, And I don't know, I mean, this might be easier than using that product rule, but you get the same answer, right? Now it's just 5x to the fourth plus 3x squared plus 6x, which is exactly what we found earlier. So just know that, sometimes there's more than one route you can take. All right, now we have the quotient rule. If u and v are functions of x and u and v are differentiable at x, and of course v of x is not equal to 0, then the derivative of their quotient, now you can see why we said v of x is not 0, because otherwise this quotient function would be undefined. But their quotient is also differentiable, and this is what it's equal to, folks. It is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. All right. So in prime notation, if this helps you, the derivative of u over v, that is u over v prime, is v times u prime minus u times v prime all over v squared, if that helps you. All right, everybody, let's find the derivative of y. Now, dy dx, dy dx is what they're asking us to find, is the derivative, not dy dx, dy dt, correct, everybody? Our variable is not x. I'm used to it being x all the time, but this time it's t. So then it will be the derivative with respect to t of a quotient, t squared minus 1 over t cubed plus 1. I always think, before I actually find the derivative, I always think to myself, can this quotient be simplified first? In this case, it cannot. And so, actually, I take that back. In this case, it can, right? T squared minus 1 is t minus 1 times t plus 1. The denominator, if you factor it, it's t plus 1. So you have a common factor. Times t squared minus t plus 1. I think I did that correctly. Anyway, I just would like to highlight that this could be simplified a little bit, but you're still going to end up having to use the quotient rule. So I'm just going to go ahead and use the quotient rule. All right, here we go. So it is the denominator times the derivative of the numerator, which is 2t, minus the numerator times the derivative of the denominator. I hope that's okay with you. All over the square of the denominator. Alrighty. So let us simplify now. Okay. So then this is equivalent to 2t to the fourth power plus 2t minus 3t to the fourth power plus 3t squared. All of this over t cubed plus 1 quantity squared. This is equal to, let's see, negative t to the fourth power plus 3t squared. I can make that a little neater for us. There we go, t squared plus 2t. Yeah, that looks good, doesn't it? All over t cubed plus 1 quantity squared. All right, folks, we did it. We used the quotient rule for the first time. All right, and that's the derivative function. Now, just a word of caution, a similar word of caution that I gave earlier, that the derivative of a quotient is not equivalent, not equal to the quotient of the derivative. That is to say, the derivative of u over v is not just u prime divided by v prime. Okay? The derivative of a quotient is not Actually, I don't like the way I wrote it. Hold on, folks. Let me write it like that. Let me change the left-hand side and maybe even make it a little more simple. So it'd be the derivative of this quotient. There, that's better. The derivative of this quotient is not equal to the quotient of their derivatives. Okay, so just be careful. All right, check out this expression for y. Y is equal to x minus 1 times x squared minus 2x all over x to the fourth. Okay, listen, if we're going to use the quotient rule here to find the derivative, we can, okay? We can because this is a quotient, so we can definitely use the quotient rule. However, it will be a lot of work. So I think what would be smart in this case is kind of what I was talking about earlier, is let's see if we can simplify the expression first and then take the derivative after that, and maybe it'll be easier. All right, so then if I simplify first, I'm going to expand the numerator. It'll be x cubed minus 3x squared. Yeah, that's right. And then plus 2x. That's the numerator. All over x to the fourth. This already looks simpler. And then divide this expression says x cubed minus 3x squared plus 2x. All of that trinomial divided by x to the fourth. So that's equivalent to saying x cubed over x divided by x to the fourth. Also, minus 3x squared also divided by x to the fourth, plus 2x, also that term divided by x to the fourth, right? Every term in the numerator divided by x to the fourth. So that would then lead us to that y is x to the negative first power minus 3x to the negative second power plus 2x to the negative third. So now that I see this expression for y, I feel like finding the derivative now of y, in my opinion at least, is going to be a lot easier. I don't need the quotient rule anymore. So dy dx will just be the derivative of x to the negative first minus the derivative d dx of 3x to the negative second plus the derivative of 2x to the negative third power, And now I don't need the quotient rule at all. I'm using, it looks like the power rule each time. Also the constant multiple rule here for these two as well. So this is negative 1 x to the power of negative 1 minus 1, so that's negative 2. Plus, now I'm changing this sign here to plus because this negative 2 comes down, and 3 times negative 2 is negative 6, but then it's a minus negative 6, so that makes it a positive 6. And this is now x to the power of negative 2 minus 1 is negative 3. And then this addition will turn into subtraction because 2 times negative 3 by the power rule would be negative 6. So this is really minus 6. And then this is x to the power of negative 4 because negative 3 minus 1 is negative 4. So I can rewrite this as negative 1 over x squared plus 6 over x cubed minus 6 over x to the fourth. Isn't that great? So if you would like, you can find the derivative of the original expression for y using the quotient rule and maybe compare that work to this work that we've just done and see which way is faster or more efficient. All right, we conclude this lesson by finding higher order derivatives. So here, they want us to find the first 4 derivatives. Now, up to this point, we've been finding the first derivative, right? We've been finding y prime or f prime of x. So we've only been finding the first order derivative or the first derivative. So here they want us to find the first derivative, then find the second derivative, find the third derivative, find the fourth derivative. Okay, so let's do it now. So then let's see. The first derivative, y prime, this is using the power rule, would be 3x squared minus, now this is the constant multiple rule and also the power rule, gives us minus 6x. This is the first derivative. Now we find the second derivative, which is y double prime. Okay, so now we find the derivative of the first derivative. We're finding the derivative of the first derivative. So then this is 6x minus 6. This is the second derivative. Now we want to find the third derivative, y triple prime, which is found by finding the derivative of the second derivative. And this is just 6. This is the third derivative. Finally, the fourth derivative, okay, we're going to write it like this, folks. We're not going to do y quadruple prime, right? We're not going to do 4 marks up here. Instead, what we're going to do is y, and then put in parentheses 4. These parentheses are important. If the parentheses are omitted, like if I would have written it like this, like that looks like y to the fourth power. Actually, that's exactly what that would mean, raising y to the fourth power. That's not what we're doing. We're finding the fourth derivative, so put the 4 in parentheses. That's how we notate or denote that we're finding the fourth derivative of y. So omitting the parentheses is something really different, so be careful. You must use proper notation. Anyway, the fourth derivative is found by taking the derivative of the third derivative, but that's just a constant, so the fourth derivative is 0. What's true is that all polynomial functions, which is what we have here, have derivatives of all orders. So in other words, we can continue if we want to find the fifth derivative, the sixth derivative, the seventh derivative, and so forth. But what would the fifth derivative be? Well, you would be taking the derivative of 0, which is just 0, right? And then the sixth derivative would be the derivative of 0, which is 0. The seventh derivative would be 0, and so forth. In other words, for this particular polynomial function, the fifth and later derivatives are all 0. Higher order derivatives have really, really cool applications in mathematics and calculus that we will explore later.